All right, when we did objects on a flat ground, the acceleration was pointed to the left. So we chose to use the X and Y directions because our acceleration would be pointed to the left in the X direction. So our forces went in the X direction, our forces went in the Y direction. So all the acceleration was in X. None of the acceleration happened in Y because it was just moving in the X direction. So one of the big ideas with free body diagrams and force equations is that you're going to choose your coordinate axes such that one axis always points in the direction of acceleration. The other axis is going to be perpendicular to that axis, and it should have an acceleration of 0. The last thing you want to do is deal with components of acceleration. That is really awful. So one axis always points in the direction of acceleration. So suppose we have an object on a hill, and our object then is accelerating down the hill. If we put our set of axes, X and Y, in the middle of our hill, the only force that lines up is going to be mg. We're going to have components of normal force, and our acceleration is going to have both an X component and a Y component. That is really, really terrible. So instead, we can change our universe and tilt our axes so that they are pointed to line up with the acceleration. So now my downhill axis lines up with my acceleration. There is no acceleration in my axis that's running perpendicular to the hill. All of the normal force points in this axis, and the only force that has components is our mg force. Way easier to deal with. So first step when we're dealing with objects on a hill is choose a coordinate system. You can call this X and Y if you want to. Khan Academy, if you watch any of those videos, that's what they will do. This will be X direction, this will be Y direction. Totally fine if you do that. I call it the parallel direction for the direction that's parallel to the motion, and the perpendicular direction, the direction that's perpendicular to the motion. But as I said, you can call it X and Y if you want to. So the normal force is pointing in the perpendicular direction, the acceleration is pointing in the parallel direction, and the force of gravity is in both directions. So we have to separate that into components. So when we do this, our axes are going to run perpendicular to the hill, so along the normal force, and then along the angle of the hill. If we draw the components of our mg vector, then we've got the cosine, or let me back up. This angle here is similar to this angle here, and you can prove that using geometry if you want to, or just take my word for it. But this angle here is going to be the same as our hill angle. So if we do the cosine of this angle that's adjacent over hypotenuse, and then if we solve for that component, it will be mg cosine theta. So it's really similar to what we did with finding the components of Vx and Vy when we were shooting things up and in an angle. And also very similar to what we were doing with equilibrium when we found components of those vectors. The opposite angle, opposite over hypotenuse, the sine of that angle, is going to be our our parallel component, so mg sine theta. That has to point down the hill. In fact, that's the only force that points down the hill, is that mg sine theta, as long as there's no friction. So then we write our force equations. So in our perpendicular direction, we have normal force going up. I've defined that to be the positive direction. And we have mg cosine theta going down. So we have normal force minus mg cosine theta. That's the sum of our forces. That's going to equal ma. But because there's no acceleration, it's not hopping up and down off of the ramp, that's equal to 0. In the parallel direction, we only have one force, and that's mg sine theta. And so that is going to be equal to our ma.